One of the ways we can figure out the empirical formula of a hydrocarbon is by burning it in excess oxygen. It's a little more complicated to try to figure out the formula, so there's several steps, but we'll take a look at it. The device to figure out how to burn it in oxygen is called a callioparrot, or a Liebig tube. It was first designed in 1830, and it's designed to measure tiny amounts of carbon. Whatever you're burning is burned, and then the CO2 comes and bubbles through some potassium hydroxide. The CO2 is absorbed into the potassium hydroxide solutions, so there's a lot of bubbling here and a lot of bubbling here, and by the end there's practically no bubbling, showing that all the CO2 has been absorbed. By weighing this before and after, they can figure out the amount of CO2 that was absorbed. It's also possible to absorb the water, and we'll talk about that in a minute. It became such an important piece of equipment in the 19th century that it appeared everywhere, and it is still shows up today in the American Chemical Society's logo. When we try to figure out the empirical formula of a hydrocarbon by burning, we're either going to use something that's a pure hydrocarbon or something that contains carbon, hydrogen, and oxygen. Things like aldehydes, ketones, carboxylic acids, etc. The sample is burned in oxygen, and then in case there's some incomplete combustion going on in which the product would be CO, we have a catalyst to turn the CO into CO2. The water is absorbed by magnesium perchlorate, which is hygroscopic. Hygroscopic is an important word, meaning it absorbs water from the environment or the atmosphere. And then all that should be left is carbon dioxide, which is absorbed into the KOH, and you saw that on the previous slide. If we know the amount of CO2, then the law of conservation of matter can give us the mass of carbon in the original. Each CO2 has one carbon, which has 12.01 grams per mole. All CO2 has a molar mass of 44.01 grams per mole. So that percent times the mass of CO2 given in our problem tells us the grams of carbon in CO2. Law of conservation of matter says it's also the grams of carbon in our original compound. We can do something similar to get the amount of hydrogen in our original compound. Each water contains 2 hydrogen atoms, 2.016 grams, and the molar mass of water is 18.02 grams, so that fraction times the mass of water given in our problem tells us the mass of hydrogen in the water. Law of conservation of matter says that the mass of hydrogen in water is the same as mass of hydrogen in the original compound. Oxygen doesn't work that way. It's a little more complicated, but we'll take a look at it. So let's see an example. I have a 2.25 gram sample of a compound. It has only carbon and hydrogen, and its molecular weight is 16 AMU. That's saying atomic mass units. It's another way of saying its molar mass is 16 grams per mole. It's burned in oxygen, and we know how much carbon dioxide and water are formed, so we want to know the molecular formula. So we start off by writing the equation and figuring out our givens. We know that there's 1/4 gram of hydrocarbon. We know that there's 0.784 grams of carbon dioxide, 0.642 grams of water. So let's try to figure out how many grams of carbon are in our original substance. There are 12.01 grams in carbon, 44.01 grams is the molar mass of carbon dioxide, and I multiply it by the mass of carbon dioxide to give me 0.2139 grams of carbon in my carbon dioxide, which must mean there's also 0.2139 grams of carbon in my original compound. I'll do the same with water. There's only 3 sig figs in this problem, so I shortcut it a little bit and only used 3 sig figs in my hydrogen. There's 2.02 grams of hydrogen for every 18.02 grams of water. Multiply that by my mass of water to figure out my mass of hydrogen in the water. If that's my mass of hydrogen in the water, 0.07197 grams, then that's the mass of hydrogen in my original compound. Now it's just like doing any other empirical formulas problem. First thing I have to do is convert it to moles. Once I've converted it to moles, I divide both by the smaller. If I had a longer piece of paper or longer screen, I would do it right here, but instead I'm going to do down below. Divide both by the smaller, which in this case happens to be the carbon, and I end up with 1 carbon and 4 hydrogens. So my empirical formula is CH4. The problem said find the molecular formula. So let's figure out the empirical weight of CH4. Carbon is 12. And each hydrogen is 1.01. So it turns out that my empirical formula and my actual formula are the same. This is methane. Now let's take a look at a second problem. In this problem, we have 4 grams of the hydrocarbon, but now it also contains oxygen. We'll write down what we know, but here we have to be careful. I know the amount of carbon in CO2 is the amount of carbon in my original compound. I know the amount of hydrogen in water is the amount of hydrogen in my original compound. The amount of oxygen over in this product side, it's the amount of oxygen in the compound plus a completely unknown amount of oxygen from the atmosphere. So we have to do a little more work to find the amount of each element. Now this one, instead of finding the whole empirical formula, we're just going to find the percent. So to find the percent of carbon, we will start with our 12 out of every 44 grams of CO2 is carbon times the grams of carbon means that I have 3.06 grams of carbon in carbon dioxide, which means I must have had 3.06 grams of carbon in my original reactant, sorry. And I can do the same with hydrogen. 2.016 grams of hydrogen for every 18.02 grams of water times the original amount of water means I have 0.257 grams of hydrogen in my water, which means I have 0.257 grams of hydrogen in my original compound. By dividing them both by the original mass of the compound, I can find the percents of carbon and hydrogen. So I have 76.4% carbon, 6.4% hydrogen, but I still don't know the oxygen. I can't use any information over here on the right to figure out how much oxygen, but I can still use the law of conservation of matter. If 76.4 and 6.4 are accounted for, that's 82.8, the other percent has to be oxygen. So I know that 17.2% of my original compound is oxygen. Once I have these 3%, then I can use an empirical formula problem just like any other empirical formula problem. Divide by the molar mass, divide by the smaller to find the smallest whole number ratio. So let's try that with this problem. We now know the percents of carbon, hydrogen, and oxygen. So pause the video, and when you're ready and you think you have the empirical formula, we'll take a look at it. Okay, you ready to go through it? First thing I did was to convert all my amounts from grams to moles. Using the molar mass of carbon, hydrogen, and oxygen. Then divide by the smallest, and I don't know why those aren't written there, so we will add them in. There they go. And we end up with numbers that are not really one of those fractions we looked at. Remember, this is an experimental science, and there could be small amounts of errors. So 5.9 and 5.96, those are really 6. The formula is C6H6O. So in your homework, there are several problems that give you the chance to find empirical formulas either straight or through combustion. There's one more that I want to take a look at, and that's trying to find the empirical formula of a hydrate. So that's the next video.